Howdy nerds. Here's that video I was promising you about to try to help you with the extra credit properties and characteristics of functions. I have a lot of students that are still needing help with the increasing, decreasing, positive, negative, and domain and range, brackets and parentheses type stuff. This is going to include in-behavior material, asymptotic behavior material, and we'll end with some finding the domain of a function algebraically. Hopefully I can get it done in one take because, well, I printed in color and I'm writing it in pen. Okay, let's see. Find a good pic. This color feels good. Alrighty, so here we have a graph, and here's what I need you to see. This graph has a dot on this end closed and a dot on this end opened. All right, so this graph does not go on forever. You're looking at this entire graph. There it is. So when you say the domain, what you're saying is, which of these values right here on the x-axis, which of these values does this graph exist for? So you're taking a walk down this line, you're looking up, you're looking down, and you're looking to see if you can see your graph above you or below you. And as long as you can see your graph above you or below you, then you are on the domain. So let's start out here at the left because everything is left to right. So we start our trip from the left, we start walking, scoot, doodle-doodle-doodle-doodle-doo. Oh, hey, look, there's our graph, okay? So the very first time we can see our graph is at this x value. So that is where our domain will begin. And since that is a closed dot, we will say the domain begins with a bracket at x equals -7. Now after -7, we keep walking, and we're looking up or down, and we're looking to see if we can see our graph. So our graph is under us, under us, under us, under us. Up, we stepped on our graph. It's above us, above us, above us, above us. No holes. Above us, above us, above us, above us, and uh-oh. This is the last time we see any hint of our graph, right there at x equals 9. The problem is, at x equals 9, this graph does not exist. So since it does not exist above or below at this value, but it was the last hint of our graph, put an open parenthesis. You will never bracket an open dot. If ever you have to do something with an open dot, it'll be a parenthesis. So domain is you taking the trip down the x-axis and looking up or down. Range is the same kind of idea. It is still small numbers to big numbers, but this time we're taking our trip on the y-axis. Small numbers requires us to start at the bottom. So this time we're climbing the y-axis like a ladder, and our job is to look left or look right to see if we can see our picture. And as long as we can see left or right and see our picture, see our graph, then we are on our range. So you climb the ladder, bloop, 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 right there. You do have graph to your left, right there. And it begins with a closed dot, so our range will begin with a bracket at a y value of -10. Now you climb this ladder, looking left, looking right. Graph is to my left, 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 up, I hit my graph. Now I go up, it's to my right, to my right, to my right. Now right here, some students are getting a little bit confused as to what to do right here. Because there's a hole in the graph right there. But can you look to your right and see the graph anywhere? In fact, could you look left or right and see the graph anywhere? If you go left or right and you can see your graph, then you are still on the range. So there's a hole in the graph right there. I'm aware of that, but look, your graph is still right here. So this y value is not a problem for us. We do not need to mention this y value because it's part of my range. And it's not the top of my range because I could keep climbing this ladder and still see graph. The last time I see graph is right here at this y value, at 8. Now this, just being a piece of the graph that is not an open dot, implies a closed dot. This graph does hit y equals 8 and never goes above y equals 8. That is why that's its range. Range is the only time you will put a list of numbers in interval notation that are y values. Every other interval notation is x's. This is the only time you'll do a list of y's. Now positive and negative are a list of x values where our y values are positive or where our y values are negative. But again, we're using the x's to describe when our graph is above the x-axis or below the x-axis. Has nothing to do with growing or falling. It's literally, are my values here positive or negative? And when we say that, we're asking about the y's. Are my y's here positive or negative? So we begin at the edge of our domain. And right here, my y values are negative. So we'll switch colors. We begin at x equals -7 with a negative y value. And the last time as you head to the right that you can see your graph be quote-unquote below you is here-ish, immediately to the left of right there. Because right there you step on the graph. But right here, when you're on the x-axis, this graph's y value is 0. 0 is not a negative number. So what you have to do is you have to say it stops being negative at -5. But it does not have a negative value there. It is a value of 0. So I can't bracket this number because it does not have a negative value. Now this is the only time our graph is below the x-axis. The rest of my domain, my graph is above the x-axis. So for the rest of my domain, from here to here, my y values are positive, which means I'm going to list from -5 until the edge of my domain. And my domain comes to an end, like we said, at 9, and since that dot doesn't exist, it's parenthesis. Let me grab the purple pen. Now we're talking increasing, decreasing. This is once again a list of x values. But now we're talking about, is the graph going up or is the graph going down from left to right? And this is where we pretend that we are on a roller coaster. And this car is going that way because it's going from left to right. So this point, because it is an end point, will be bracketed for increasing, decreasing. But that's only because it's an end point that is closed. Now, hoping you could see, using this little arrow, that right now my graph is heading up, which is increasing. So we begin increasing at -7. But when does this roller coaster stop going up is the question. Well, the answer is at this value. That is where my roller coaster stops going up. And right there, if you got the picture of your roller coaster, as long as you couldn't see your hair blowing in the breeze, it would be hard to say if the roller coaster was going up or going down. And because of that, we're going to say it's doing both. At this x value of 5, I stopped increasing, and I started decreasing. And I decrease until the end of my domain, which is at that 9, but because that 9 doesn't exist, we can't bracket it. So I hope that it's simple on a graph like this. I tried to keep this graph simple. And then as the examples go on, I make the graphs a little bit, quote unquote, more difficult, okay? But we'll start with the simple one to get the ideas. What are maximums and minimums? They are places where our graph has a low value and places where our graph has a high value. High values, low values. They typically happen when your graph stops increasing and starts decreasing, or you could say stops decreasing, starts increasing. But they happen at tops of bumps and bottoms of bumps. The only other place that minimums and maximums can occur are at endpoints. Endpoints that are closed are always an extreme value. They are always a minimum or a maximum. This one is closed. That makes it a minimum. So a minimum, let's say, of y equals -10 at x equals -9. This is the minimum value. This is where it occurs. Do we have a maximum? Absolutely, right there. I have a max value of y equals the top of my range, and it occurs at x equals 5. Now let's talk about this. Can this be a minimum value? No, it cannot. How come? Because it doesn't exist. This point doesn't exist. That's what that open dot means. Okay? So I'm hoping that the simple example helps clear up how these things are to be done. Because now I'm ready to step up the game. Make the graph slightly more complex. All right? Notice I didn't worry about increase or a maximum or minimum on this one. The reason why is because it has no endpoints. And this one actually does not have a maximum or a minimum. That arrow and that arrow tell us that the behavior that we observe there, it will continue forever. I actually put the dotted horizontal line on here. This is a horizontal asymptote. This arrow means my graph will forever go to the left and will forever approach this dotted line. This one, you could see, I made sure you saw that it went past this 4. That means this down and to the right behavior never stops, and it will continue to be more and more to the right. Yeah, it goes down really fast, but it does still keep going to the right. So try to make that obvious. And oh, look, there's a hole in the graph right there. How about that? Okay, domain. Domain is you're taking a trip on your x-axis, you look up, you look down, you look to see if your graph is there. This left arrow tells me this graph never stops going this way. And far left on the x-axis is where we find negative infinity. Now we're taking our trip to the right. Boop, boop, and we're looking. Is the graph above me or below me? Above me or below me? Above me or below me? Yes, 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 yes. Right there. This graph was a ceiling for me the whole time. It's kept me out of the rain. And then for some reason, there's a hole in the roof right here. I look up, hole in the roof. I look down, there's no graph. That means at x equals 2, I'm no longer on my domain because I do not have graph at this x value. And that point doesn't exist. But is there graph after x equals 2? There darn sure is. So you use a union symbol to say there's more. And then we go, okay, where does it begin again? Well, it begins at that hole. And to the right, it never stops going to the right. And that is where positive infinity is on the x-axis. Mr. Emmons pointing down, I'm aware, but down is a y idea. These are x's only. It goes to the right forever. Now you want to worry about the y ideas? It's the range, okay? Range is you climbing the y-axis as a ladder. And as you're going up the ladder, you look left and right. You look both directions to see, can I see my graph? If yes, you're on the range. If no, you're off the range. So we're climbing our ladder, and you know what? This downwards arrow tells me it never stops going down. So my range will begin at negative infinity, the downwards negative infinity. This is the left negative infinity. This is the down negative infinity. Now I'm climbing this ladder, up, 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 okay, and I can see this graph is to my right, 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 to my right. I look to my right, I see a hole. I look to my left, there's no graph. That means at this y value, my graph does not exist anywhere. See, that's different from this one. See, right here, my graph didn't exist, but it did still exist for this y value right there. I could see graph. Yeah, there's a hole out there, but I could still see graph. This one, I can't see graph in either direction, so that number is not on my range. But is the graph immediately above that y value? Well, there sure is. So you begin at that number again. And you go until you hit the top of the graph. And you know what? This red dotted line is acting as a ceiling for the y's that the graph will never reach. So yeah, 3, excuse me, is the highest y value that the graph thinks about, but unfortunately it'll never reach it. It wants to. It's the goal. It's going to always reach for 3, and it'll get infinitely close, but it'll never quite reach it, and that is why we can't put a bracket there. So instead we put a parenthesis. Now positive and negative we talked about last time with the last example. Positive means when is my graph above the x-axis, because that's where positive y's are. Negative means when is my graph below the x-axis, because that's what the negative y's are. But we only use x's to describe intervals. The only time we use y's is range. Everything else is a list of x's. So let's see. To the left of our domain side, we're out here to negative infinity. That graph is above the x-axis. Now we head to the right, and we make sure that we're tracking our graph. It's above me, it's above me, it's above me, it's above me. It's still positive, positive, positive. Oh, that's right. The graph doesn't exist here. So it can't be positive there because the graph doesn't exist. So this interval is going to have the same gap in it that the domain had. But is my graph above the x-axis still immediately to the right of this? Absolutely is. When does it stop being above the x-axis? When it hits the x-axis, right there. So we have to estimate this number. And I would never make you estimate with fill in the blank. It would only be with multiple choice. So we'll say that this is about, looks like it's past 2.5, so call it like 2.6-ish. And remember, when you're on the x-axis, your y value is 0, which is neither positive nor negative. So the boundary for positive and negative will never be bracketed. And that's where my graph starts being negative. And you know what? As I go to the right, this graph will always be below the x-axis now. Okay. Now let's talk about increasing, decreasing. And instead of using words, I'll actually write the intervals. So we always look at domain values. So we begin out here, and we go, if this was my roller coaster, it would be slow, but it would be slowly coming down. Or imagine you put a marble right there and let it go. What would it do? It's clearly going to go down as it goes to the right. So it's decreasing. Falling, falling, falling. Oh, don't trip, there's a hole in the graph. Falling, 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 falling. You know what? This graph never increases as it goes from left to right. So I'm just going to write none or never. I'll write never. But for decreasing, I could cheese it and I could just write the words entire domain, or I can write the domain. So I'm going to go ahead and write the domain because on my test, you will have to answer this with an interval. So I'm going to go ahead and write an interval. And I'm writing the entire domain because this graph is always decreasing. There it is. Let's take these basic example skills and try to apply them to a more advanced skill example. I don't know how to say it. This example's got some crap going on, okay? So let's see what's going on. I've got arrows here, 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 there. Man, I got a hole in my graph right there. I got an endpoint right there. I got 2 vertical asymptotes. I got a horizontal asymptote. All right. So far in these 2 examples, the only time you saw a domain problem was at a hole in the graph. A hole in the graph is a place where the graph does not exist for x values. Another way to see where an x value does not exist is a dotted line like that. A vertical asymptote is another place where the graph simply will not exist. So one more time for our x values, graphs don't exist when there's a hole, and for our x values, graphs don't exist when there is a vertical asymptote. Usually will be on there as a dotted line already so that you know for a fact where that number was. So when I go to write my domain, I cannot mention x's where there's a hole or where there's a vertical asymptote. Okay, domain. I'm going to have to write it underneath because this domain is going to be lengthy. This left-hand arrow tells me I never stop going left. And to the far left is where we find negative infinity. So we start taking this walk on the x-axis, looking for the very first time where graph doesn't exist. Up, graph doesn't exist. There's a hole in my ceiling at -5. But does the graph exist immediately to the right of -5? Sure does. Look, there's more graph after -5. And you walk until you find another number where the graph doesn't exist for x. Right there. See, this goes up, but it does go to the right. It's going to get closer and closer and closer to this line, but not touch it. So the graph also does not exist at x equals -3. But is there graph to the right of -3? There darn sure is. It just happens to be down here. But I don't care about the fact down here because that's a y idea. All I care about the fact is that there is graph to the right of -3. Still graph, still graph, still graph, still graph, still graph, no holes. Oh crap, another vertical asymptote. Graph will never reach x equals 3. But is there graph to the right of +3? There sure is. It's over here. And yes, this arrow points up, but it will be infinitely close to this red dotted line, and that's why we put the 3 there again. And then graph stops existing at x equals 4, which is a closed endpoint bracket. See, told you that domain was long. The range is going to be the y values where the graph does exist. And I guess I'll have to write it up here because I really didn't leave myself enough space. So I'll put the range up here. In fact, let me just D for domain, and I'll do like range like this. Sorry about the space. Okay, range. This is the only time we use intervals for the y values. Looking from the bottom of the x-axis, there is no such thing down here, but you see these two down arrows that tell me this graph has no bottom, so it will be coming up from y equals negative infinity, equals negative infinity. You can never equal negative infinity. We climb the ladder, we look left or right, and as long as we can see our graph, we're happy. I see it, 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 uh-oh. Okay, at this value of 0, of y equals 0, my graph came to a stop. Because look, immediately above it, no more graph. So I have to do this. And this is y equals 0. But that does exist right there, so it's a closed dot. Is there graph north of x equals 0? Excuse me, y equals 0? There darn sure is. Look, it's up here. Union. But what's the next lowest value that I can attempt to see my graph? There's nothing, no graph between here and here. The next time I think about my graph is this one, right there, that y value, but it'll never reach that y value. There is graph above it, but okay, hole in my graph to my left, I look to my right and crap, there's no graph. So this time, this hole in the graph is a range problem because I look left, hole, look right, no graph, there is no y value at y equals 2. Is there graph above 2 to the left or to the right? There sure is. Look, here's some right here. Okay. And some people get tripped up right there. But you don't need to get tripped up right there because your job is to say, if I look left or right, can I see my graph? And it's only left, only left. Okay, now it starts being on both sides, both sides, both sides, both sides forever. And never stops being on one of my two sides. All right. Positive and negative is when your graph is above the x-axis or below the x-axis. I think it's incredibly obvious that this part right here is the only part that could be below the x-axis. So starting at this x value, because remember we're only using x's from now on. Range is the only time we use y's. So starting at this x value, oops, did I say positive? Poop. Negative. This is where the negative values are. Okay, so let's fill that out first because that's easier. They start here at x equals negative 3. And they're always negative between negative 3 and positive 3, except right there. Because right there, this graph is on the x-axis. That is y equals 0. It does not have a negative y value. So at x equals 0, I hit y equals 0. But immediately to x equals 0, my y values become negative again, but I can only go to 3 on that side. So I can't just say from here to here. I can't do that because right there I do not have a negative y value. And that's why I had to hop over that point. The rest of this graph's domain, every other part of the domain is positive domain. So that is going to be this entire piece and this entire piece. So this one was negative infinity up to the number negative 5, but did not exist at negative 5. Existed after negative 5, but only until negative 3. And there is one more piece of this graph that is above the x-axis. That's this piece right here. And this piece right here was this one. Get skinny math. Suck it in. You can fit. There we go. Alrighty. Increasing, decreasing. Roller coaster going up, roller coaster going down. If you put your roller coaster car right here and you had to go to the right, it's got to go up. So this whole piece, the graph is going up. Remember, you have to hop over that number. There's me hopping over x equals negative 5. And it keeps going up from after negative 5 until we get to negative 3. Now we look around and we look to see, are there any other places where our graph is going up? And you know what? There is. This piece right here is going up. This piece of the domain was negative 3 until 0. But at x equals 0, my graph starts to go down. So this point right here, we call it a turning point. This point right here is a place where my graph changes the up-down behavior and exists. You see, it doesn't exist here, so I can't change there. And it doesn't exist here, so I can't change there. But it does exist there, and it changes behaviors. So that's why we get a bracket there. Now it's decreasing and decreasing. So this thing decreases for the rest of its domain. I'm just going to, for space purposes, come down here. It starts decreasing at x equals 0. And it decreases forever as it gets closer and closer and closer to x equals 3. Can't include x equals 3 because that x value doesn't exist. But if you look immediately to the right of x equals 3, your roller coaster is still falling. And it falls until it hits the end of the domain. Like that. Very complex example. Okay. I'm going a little fast, but that's because you have the ability to pause if it's a video at home, right? So, for this graph, we're talking about in behavior and asymptotic behavior. In behavior specifically is talking about the left and the right arrows. We have two of them. We'll call this arrow 1. We'll call this arrow 2. Arrow 1. That arrow is going left. So as x goes to the left, it's going to get more and more negative. That's negative infinity. But you can see also that arrow's headed downwards. And as you head down, the y values are going to negative infinity. For end number 2, this one out here, I'm going to the right. So x is approaching the right side of that number line. It's never going to stop going that way. X is going to get bigger and bigger and bigger, so it's going to approach positive infinity. The y values are going up. And if you climb the y-axis, up, 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 you find positive infinity. There it is. Now, asymptotic behavior, I kind of goofed a little bit in the notes, and I called it a type of ending, but it's not. Asymptotic behavior is approaching these vertical asymptotes if they exist. Now, I know it looks like it's touching it, but it's not. It's just Desmos pixels, things like that. Okay, it's not actually touching it. Asymptotic behavior. Let's say I have one of them here and a second one here, always going from left to right. So my first asymptotic behavior is this arrow right here. Now, my x doesn't get to go to the right forever because this green line gets in the way. So what I say is x is approaching that value. But the problem is I could be either on the left side of that number or on the right side of that number. If I'm on the left side of it, I'm at a number that's actually smaller than -1. We put a little superscript of minus to mean but smaller than that number. My y values, well, that graph is shooting down. We've already said what happens as we shoot down. And then here, the second one. X is still approaching this green line. X is still approaching -1. But this time, I'm on the right side of it. If you're on the right side of a number, you're at a value that's slightly bigger. And that's why we use that little plus as a superscript. And for that one, my y values are skyrocketing up to positive infinity. There you go. So end behavior will always be a left or a right arrow. Asymptotic behavior will always be a left or a right of a vertical line. Now, some endings do approach, where is it? A horizontal line. This one approaches a horizontal line. Now, I didn't ask us for this end behavior, but we could do it. I'm going to go ahead and write it on there real quick. And I'm going to write it in this little space. As x goes to the far left, my y value is attempting to reach this y value. But I'm underneath that y value, which is a smaller number. So yes, your end behaviors can approach horizontal asymptotes where you'd have to use plus minus notations, but it's more often used for, where is it? Vertical asymptotic behavior, okay? And lastly, whoo, this video is long. I've already reached 30 minutes. I'm so sorry. Luckily, you can pause and move and go in and out and backwards and forwards and whatever you want to do. It says, find the domain of each of these functions, respect all the rules, put the domains in interval notation. What do I mean by respect the rules? Two things matter. We have two rules. You cannot take the square root of a negative number. Big fat no-no. You cannot ever divide by 0. Big fat no-no. Those are the rules. We have to respect those two rules. And sometimes, sorry, you couldn't see it. Sometimes we have to do both rules at the same time. So first, let's look for square root bars. I have a square root bar right there. I have to make sure that whatever is underneath that square root bar, what colors do I want to use? Let's use blue for this stuff and go Gators. Orange for this stuff. Hopefully you can see that those aren't the same color. They're not. But I'm going to use blue and I'm going to use orange. Okay. So underneath the square root bar can't be a negative number. But what is not negative? Not negative is positive, so greater than 0, or 0. So we know because of the blue stuff, x has to be greater than or equal to 0. Well, that was easy. There's nothing to even do with that. Okay, that part's written. Now, the bottom of my fraction has the ability to be 0, but it is not allowed to be 0. So we say, all right, x minus 3 can't be 0. Let's go ahead and add 3 to both sides. I know that x can't be the number 3. Now, that is an issue for us. If you were to shade a number line, in fact, I'm not going to ask you to shade a number line yet. That'll be for a later chapter, but let's go ahead and put these two things onto a number line. It might help you actually write down the answer. The first thing that mattered to us was the number 0. Picture not drawn to scale because who cares? And then what happened was we cared about the number 3 as well. What we know is my answers begin at 0 and include 0. And then go to the right. However, I can't use 3. So I do that. So it's all the shaded stuff. And now that it's like that, maybe it'll be easier for us to understand why the interval notation for this domain is beginning at and including 0, up to the number 3, but not including 3. However, I am immediately to the left and to the right of 3, and I never stop going to the right. That is why that is the domain for that fraction. Next, notice that neither of my rules cares about the top of the fraction. So the fact that there's an x up here means nothing to me. I don't care. I care about stuff inside square root bars. I care about bottom of fraction. That's all I care about. So, first, this is inside a square root bar. That number, x plus 4, cannot be negative, and which means it could be greater than or equal to 0, right? Up. Hold on a second. Well, you know what? Let's just go ahead and solve that real fast. Let me subtract a 4 from both sides. It tells me x is greater than or equal to negative 4. Up. Watch out. The bottom of a fraction cannot be 0. Oh, right here I said it could be 0. X plus, so the whole square root thing. Square root of x plus 4. Oh, that was supposed to be an orange. Pooh. Let's try this again. Square root, and I'm running out of space that way, so I'll do it here. Square root of x plus 4 cannot be 0. Well, you get rid of square roots by squaring because they're the opposite of each other, like that. And what that gives you is that x plus 4 cannot be 0. So if you subtract that 4 from both sides again, what you get is that x can't be the number negative 4. So this says it could be negative 4 and bigger. This says, oh, you can't use negative 4. So if you put that on a number line, I cannot close dot this -4. Oh, but it is okay if it's bigger. So the only way to be respectful of both rules, the only numbers that are cool with this and cool with this are these. So our domain then is beginning at not including -4 to infinity. Now what I'd like you to see though for this very last one, for this remarkably long help video, oh my gosh, I'm so sorry. It's just I want everybody to really get this stuff, is the exact same fraction, but it's flipped upside down. Let's see what happens. First, I cannot take the square root of a negative number. That means the stuff inside the square root bar cannot be negative. It could be greater than or equal to 0. Is it a problem if x plus 4 equals 0 this time? No, it's not. Why? Because it's the top of a fraction. There are no rules about the top of a fraction. Look, I can put any stuff up there I want. But if you subtract this 4 from both sides, you once again get x is greater than or equal to -4. We have to respect the fact that we have a fraction as well, and down here better not be equal to 0. So x minus 2 cannot be 0. If we add this 2 to both sides, what we get is that x cannot be 2. So if we put it on a number line, and remember, I don't need you to put it on a number line. This is just to help you. This says begin at and include -4. This says do not include the number 2. Begin at and include, then go to the right. So I'm going to the right, going to the right, going to the right. Uh-oh, can't use 2. Boink. So it looks like our first graph did on our number line. With a completely different type of setup, we still have a domain that begins somewhere, has to hop over another number. Is this the only way these kinds of things can happen? No. You could have to hop over several numbers with unions. It happens, you know. There is no patterns, there's no way to memorize anything. You just literally set up both rules, respect both rules, and imagine you put it on a number line to get your answer. And if you can't imagine the number line and you need to see it for now, fine. Draw the number line. Just know how to do it and do it correctly. I hope that this has cleared some things up for you, and I hope that we're all going to crush this test next week on this material. If you have any questions, please ask me in class or shoot me messages so I can get right back to you over Thrillshare. Alrighty, nerds. I'll see you later.